Hey, welcome back. It's Alan. All you calculus connoisseurs, we're going to jump into chapter 2, which I titled Pushing the Limits. We're going to talk about this new concept in calculus, the first calculus concept called a limit. So I wanted to quickly show you the outline of chapter 2 here in all the 5 sections that we have. The first one we're going to start with is a preview of calculus. So just an introduction now that we've gotten chapter 1 and quite a bit of review out of the way for us to make sure that we can understand these calculus concepts even better. All right. So just preview of calculus in this first section. There is quite a bit in it though. So I'm going to go very quickly in this section, maybe not explaining everything, letting you guys read through it and then trying to fill in those blanks ahead of time as we always should. Here we go with chapter 2, section 1. So we're going to introduce what calculus is with a few questions. Again, please read through this in its entirety. See if you can fill in as many of the blanks that are possible, and then we'll go through them, some more quickly than others. I'll stop and explain things that I feel like need further explanation other than the text itself. Don't forget, you can also look these things up in the ancillary textbook that I used a lot of the things in sections and design from, and that's that OER OpenStax Calculus Volume 1 text. Right? So why did we learn so much algebra? Why do we have a whole chapter previewing and reviewing? Well, there's two main questions that people set out to understand in depth and in more detail. So the few blanks that we're going to fill in here are, how do we find the rate of change of nonlinear functions? This is known as the tangent problem. The second was, how do we find the area enclosed by a curve? This one is obviously called the area problem. So these were two of the main questions that propelled people to start exploring a new realm of mathematics. Actually, there was two mathematicians. They were named Leibniz and Newton. And those two fellows actually, astonishingly, discovered this on different parts of the planet around the same time. Pretty amazing stuff, right? So they get a lot of the credit, even though there was predecessors that started these inquiries. So we're going to go ahead and start with this first question. And I'm going to start this by giving you guys a quick demo and explanation via some slides that I created in GeoGebra. All right, so let's go check that out. All right, so I've pulled up my GeoGebra slides here. I got 4 of them. We're going to run through real quick and try to give an explanation of that first question of calculus. How do we find the slope or rate of change of, say, a curve? So let's start with the basic function like y equals x squared. And if I asked you to find the slope, it's kind of weird, isn't it? Because if I gave you a line like this, you know the slope of a line and you know it everywhere. Pick any point, or even given the equation, y equals mx plus b, you know that already the y-intercept is here, and the slope is up 1 over 2, up 1 over 2. Every single point on this thing has the same rate of change, the change in the y's over the change in the x's, rise over run, if you will. But what about this? How could you find the slope of a parabola or any curve? Well, let's take, for example, that point right there. We know at this point right here, we can draw this, what is called a tangent line, and we know on a line that we can find the slope or rate of change that we were exploring in chapter 1. And so we can tell definitely that at this point right here on our curve, that the slope is negative. The problem is, if I pick a different point, say over here on the right side of this symmetrical parabola, now my slope is positive. So you can see that the slope is different, and not just negative to positive. Let's pick a different point on the other side. Let's say C here in green. You can see that this line is even more positive than this one. So not only are they both positive on this side, but they're different. So these are the questions that people were pondering And not just lines and their rate of change, but what about different types of equations or functions? So let's take a look at another scenario. Let's take a look at a circle, which is not a function. We know it's not a function because it doesn't pass that vertical line test, nor would its inverse be because it fails the horizontal line test. But this still has an equation, and we may still want to know the rate of change. So again, we can always find the slope of a line. And what do we need in order to find the slope of a line? Well, we don't need just one point, which is called a tangent. We would need a second point on this line. Now, this is not a good point. As you can see, it's not on my grid here, where I know it's over 9, but it's not up a good amount of y, maybe like 5 3/4. So that would be one point that we could work with, but it's not very good. Not to mention, if we scroll down this line, do you see another good? Well, that's pretty close. That one looks pretty darn close to 14,0. I'd have to zoom in and see, or have the equation of that line to actually find it. That's no good, because the one thing that we're usually given is the equation of that graph, that equation or function. What we need in order to draw a line is 2 points. And do you guys remember what it's called when a line intersects another graph in 2 points? It's going way back to geometry. Tangent was when it only hit once, a secant line if it hits twice. And so what we're going to have to try to do is find the slope of a line. But the problem is we don't want to select 2 points. We actually want the slope at a specific point, because then that tells us the rate of change or slope on my equation or curve at that specific point. We could find the slope on this blue one, but is it of that point or that point? So let's take a look at the third slide and see what we're going to try to do is take either this point and move it to the other one, or this point, until we get so close with our 2 points that it looks like they become 1, just like our tangent. So let's go back to our y equals x squared parabola that we started with in answering this question. What if we had y equals x squared, and let's just pick a point. Let's go, now notice I've blown this up so it looks like it's even wider, but still my y equals x squared curve. Let's go at 3. Let's pick that point. And what if I wanted to find the slope of this curve at 3? Well, to find the y value, we'd square it and get 9, and that would be the tangent line. Now again, we could pick another point on this and try to find the slope. The problem is we want to generalize this. Is it always going to be this easy? Is it always going to be x squared, a simple function like that? A nice point like 3, 9? No. And that's the tricky part about mathematics and proving things. You got to prove it works for everything. And you want to make it as easy and simple as possible, that whole process. So let's choose another point, not too far away from 3. Let's just go over one whole value to 4. And let's say we drew that secant line. Again, 4 squared is 16, so now I'm there. Now I can find the slope of that by simply just doing the change in my y's, 16 minus the 9, my y2 minus y1, over the change in my x's, 4 minus 3. And you can see that we would have a slope of 7. But is that the slope at this point or that point? Well, again, it's actually both of them. We want the slope at that value. We want to know the rate of change on this curve at that specific and only that point. So what we want to do is actually take that 4 and get closer to the 3. So let's go to 3.5. You can see that from the purple to the green, it's getting closer to that red line. My green point is getting closer to that red point. The problem is now I got to take 3.5 and square it to find the y value. And then to find the slope, I'm going to have to take the change in my y's over the change in my x's And you can see now we've gone from a slope of 7 to 6.5. Well, what would be better than 3.5? Let's get even closer. How about 3.1? Squared would be 9.61. Find the slope of that. Now look, from purple to green to blue, it's almost at my red. What we're doing is this process of finding the slope by getting closer and closer and closer to our point that we're trying to find, that red one there, point A. And notice my slope of these secant lines is getting really close to the slope of my tangent line in red here. And what would you guys say, based off of just these values here, that the slope of that tangent line might be, let's say, approaching? Well, hopefully you said 6, because it looks like it went from 7 as we got closer, 6.5 as we got closer, 6.1. Could we use something even closer than 3.1, 3.01, 3.00? We can get as close as we have time and patience for. We want to try to find a better way to do this process, to find that slope of 6. So what we're going to do is we're going to generalize. Let's choose, instead of a 4, a 3.5, a 3.1, let's choose any x to represent that close value. And our goal, our task, is going to be to take that x and we are going to move it closer and closer and closer. How close? So close that you cannot even tell that that line, that secant line in orange here, becomes, instead of 2 points that we need in order to find slope, it's going to become 1 point and look like the tangent. So how would we do that? Well, same way we did all the other ones. We would take the y2 minus y1 over the x2 minus x1, and that, though, would be the slope of the secant, the 2 points. And the process that we're going to call moving this thing closer and closer and closer is called the limit. And we're going to take that y2 minus y1 over x2 minus x1, and we are going to make it approach. Our x is going to approach the other x in question. That x in general is going to approach 3. And so we're going to use this symbol of an arrow as our way of saying it's approaching that. And from changing it to a secant slope to a tangent, we have to introduce this thing called a limit. That's calculus. We're actually moving things this whole process. And what do we say? What's the closest thing we could actually get to 3? Well, you could say 3.000000 and then throw a 1 in at the end. Or the closest thing that I could ever get to 3 is actually 3. The problem is, if I plug in a 3 here, you know 3 minus 3 is 0. And I would also get 0 on top, but we're okay with zeros. We can divide into a 0, but we cannot divide by a 0. But you know that before I even did the limit stuff, what do we always try to do with fractions if we can? That's right, simplify. And you know that this is the difference of 2 squares up here. And if I actually took this and factored it, I'd be able to cancel out that issue on bottom. We know anything divided by itself is 1, and anything times 1 is itself. So now we'd be left with this, the x plus 3. And if we get closer and closer and closer and closer to 3, so close that we're just going to call it 3, what happens when you take 3 and add 3? Well, we end up getting our slope of the tangent that we said it was approaching with all those other values. And that, friends, is the basis of everything we're going to be doing in this chapter 2, in a nutshell, graphically, algebraically. So let's generalize this one more time with one last slide here. Let's say we had some random function I'm calling f of x, and it's a wave, a curve, kind of looks like a sine or cosine curve, shifted a little bit. Irrelevant. What if I asked you to find the slope or rate of change? What would you have to ask me? Hopefully you said where. We need to know where I want to know. So let's just pick a point, any point, call it point A at any value. How would you find the y for that point? You plug it into the function, so f of A. And we would want to know the rate of change or slope. So we draw a line, hence the name tangent, because it only goes through at one point. Problem is, to find slope, we need 2 points. So we're going to pick a second point, call it something else. Instead of A, comma f of A, we'll call it x, comma f of x. And what do we want to do with that line? Well, we want to take it and make that x approach the value that we want to know, which is that A, so that the 2 points that we know that we can find the slope between become 1. We're going to get them to approach one another, that limit process, and get so close that those 2 points that we can find the slope of become 1. So again, this process of taking 2 points and finding the slope of that secant line will become 1 point. And so we will do the y2 minus y1 over x2 minus x1. The slope of the secant, if we make x approach some value a, gives us the slope of the tangent. So in general, we will have f of x minus f of a over x minus a. And if we let that x approach a, those 2 points get so close together that we can virtually call it 1, then that means we have the slope of a tangent rather than a secant. And that, my friends, is calculus, part 1, the tangent problem. So I spent a lot of time explaining the whole process of a limit and trying to understand why this all came about, this new form of math called calculus. And it's all about using this thing called a limit. And that allowed us to find the average rate of change or slope. So this is what we're going to explore for the rest of chapter 2. But before we do, I want to see if you guys can tell me what 1/3 is equal to. So before moving on to the next page, see if you guys can come up with what 1/3 is equal to. And I'm kind of leaving it open-ended on purpose. All right. If you need to pause it, go ahead and do that. Otherwise, I'm sure some of you are already thinking, I know what that is. I don't need to do anything. Give it a shot. Think a little bit deeper. All right, so why am I talking about something simple like 1/3? Why are we trying to take this and divide? Well, that's what a lot of you probably did. Some of you probably just wrote down the answer, 0.3333, repeating. Some of you might have actually gotten creative and tried to think of it a little bit more deeply and thought of writing it as a graph or picture, a diagram of sorts. Some of you might have actually taken 1 and divided it by 3. And we can write our 1 any way we like, as long as it's still 1. And notice that you ended up getting this repetitive pattern. But some of you may have drawn a graph and represented it like this. And which way is correct? Well, hopefully you understand that they're all the same. Whether you write it as 1/3 like that, or you do the actual division and get this. You could have even written it as 0.3 plus 0.03 plus 0.003. Bunch of different representations, but you need to know that these are all equivalent. But which way seems simplest, quickest to understand, recognize just by looking at it? In my opinion, graphing. And what I'm getting at here is there's going to be ways for me to explain things both geometrically with the graph, algebraically, or even by just plugging and chugging and grinding things out to show you how it works. And with limits, there are all 3 different ways to do this: by graphing, looking at these things numerically, and even algebraically. Which of these techniques do I want you to use? Whatever one makes most sense to you, or whatever one's simplest, considering what you're given. Now, again, I will often use this because it's easier to see and explain, but we will also have to use both of these from time to time, starting with this, hopefully getting to a quicker, easier way like this. So let's get to our first definition from chapter 2, section 1, the intuitive definition of a limit. Okay, intuitive meaning that we should be able to kind of understand it based off of what I just went over with you on the GeoGebra slides. Okay, if we make the x value as close as we can to some number we're going to call a, and the y values of our function, any function, f of x, get closer and closer to one specific number, we're just going to call capital L, because that's what the limit is equal to. Then we say that the limit exists and is written a whole lot easier without that short paragraph of explanation in symbols. And that looks a little something like this. We say the limit of our function, we'll write our function right next to it, just like a logarithm. But just like a log has a base, we want to know what our limit is approaching. So right underneath it, we're going to put what our values, since our function's written in terms of x, what our values are approaching. That's the symbol we use, that arrow. The value a is what we're approaching. And again, if it exists, then that means it's equal to some number. We're going to use capital L to represent that limit. So again, the way that we're going to say this is the limit of f of x as x approaches a is equal to some number we call L, because that is what our limit represents. So there's a key to all of this that I want to make sure that I emphasize. We have to approach the same y value, that L, if you will, as our x approaches both sides of that value a that we are approaching. Again, the key here is that we are approaching both sides of a to get that same y value we're calling L. So make sure you have that in your notes. That is the key that we will continue to go over as we progress through this chapter 2 on limits. So to help you to understand this, go ahead and take a look at this. See if you can come up with the limit of each of these as x approaches 2. And notice these graphs are not the nicest. This one has what is called a hole. This one has a jump. We're going to call it a jump discontinuity because it's not continuous. I have to lift my pen to go to the next one. This one, same thing. Looks like it has a vertical asymptote at that value of 2. All right, so go ahead and pause it and see if you can come up with, based off of our intuitive definition of a limit, what the value would be as x approaches 2. Okay, well, hopefully you were able to come up with some of these. Again, this is something that we're just introducing graphically, geometrically, so I'm not going to go into too much detail, but according to our definition, as we approach 2 from both sides, what do our y values approach? Hopefully you came up with a value of 4. Now, do we want to graph this so that we can do this? No. Do we want to plug in a bunch of numbers closer and closer to 2 from both sides? No. So we're going to find an algebraic way eventually as we progress through this chapter to be able to find this value without having the graph if it's not already there, or having to kind of plug away a bunch of numbers and do it numerically. Now, how about the next one, part B, if you will? As we approach from both sides of 2, you can see our y values approach 2 different things, which means a limit doesn't always exist. And so we will put D in E for that abbreviation. This one doesn't have a limit because as we approach from both sides of 2, you can see that our y values approach something different. And according to our definition, they have to approach the same number, just like the x's are approaching the same number. Well, then what about this third one, part C? as we approach 2 from both sides, our y values seem to just shoot up to the sky. And those arrows mean that it goes forever. So with this, which looks like there would have been a vertical asymptote, do they, from both sides of 2, do our y values approach 1 value? And if you gave yourself some time to actually think about that, yes, they do. But there's no value that we can touch or hold. It's actually an idea of the furthest value that we can think of, and that would be positive infinity. So there are going to be some issues that we run into and some weird values that we get, but these are the things that we're going to start exploring numerically, algebraically, and of course, as I just showed you, to get a better understanding, graphically. So let's start in on one and look at all 3 ways for one particular function. Let's say I ask you to find the limit of this function given here as we approach, let's say, the value 2 that we just dealt with. Trying to keep it simple here and familiar. So let's do this numerically first, then we'll look at it algebraically, and then lastly, geometrically by graphing. Go ahead and pause it and do me a favor and plug in the values that are close to the one that we want to find, which is 2. Let's start on the left side and the right side, and then get closer and closer and closer and closer to 2 from the right, and then closer and closer and closer and closer from the left. And let's see what those y values come out, and hopefully they are approaching that same value. So go ahead and pause that and plug in these values. All right, hopefully you gave yourself a chance to plug in all these values and come up with the answer. Now remember, you do have to, unfortunately, with this, plug in more values than just a little bit to the left and a little bit to the right of our 2. Because if you just plugged in 1 and 3 and you're like, oh, okay, sweet, we got the same thing, it's probably 0. Well, notice all the other values were not 0. And they were actually approaching -1. So be careful and not just jumping to a conclusion, because these are approaching from the left and the right the same value of -1 as we got closer and closer to 2 from both the right and the left side. Unfortunately, that's how we do it numerically. Let's find a better way, and let's do it algebraically next. So if we were to look at this algebraically, what does that mean? Well, if we took what we know the limit is finding, our x approaches 2, we said what would we have to approach from? Well, both sides of 2. That's the little bit to the right and a little bit to the left. And how close can we get? Well, we said really, really close. You know what? I'm going to say I'm going to get so close that I'm just going to plug in 2 itself. So as x approaches 2, I'm going to say x is 2. And because it's approaching 2 from both sides, I'm going to see if it's actually available to evaluate. And that gives us the same value of -1 that we got when we plugged in a bunch of numbers on the right and left of 2. But this was way simpler. Let's take a look at the third way that we can find these limits. And let's do it graphically. How would we graph this function? Well, as you can see here, I've graphed it for you. This is a simple parabola. Hopefully you recognize that. And again, we're looking at finding our y values given our x is approaching 2 from both sides. Remember, this is our y equals, or f of x. So we're trying to find the y as our x approaches 2 from both sides. So as we go from the right and left, our y values look like they're approaching -1. So notice we got the same value for all 3 methods. Which way was the easiest? I went in reverse order of difficulty. Okay, definitely graphing, because done. You can see it. It's easy to visualize and give the answer. Using the algebra techniques, plugging it in, we're going to get so close to 2, we actually put in 2 and evaluate to see what it comes out. And then if all else fails, we can plug in some things on the right and the left, getting closer and closer and closer to it to make sure that it's approaching the same value. So we will explore these techniques throughout, but those are the three that we will use for now. There will be some more algebraic ways that we will use as we progress for when it's not easily evaluated or unable to be, because the numeric way and graphing is not always our best if they're not already given. So before we move on, I wanted to ask you guys a few questions. Should we have obtained the same result for all those three forms? Yes, of course, if they work. And when would they work? Well, as long as we don't have any of those issues we saw earlier with those holes and jumps, asymptotes, that's where problems occur. Which of those seem to be the easiest? As I just mentioned, graphic, then algebra, then the numeric technique. And do you think these ways will always work? No, that's why there's other techniques. Which way do I want you to use? Whatever's easiest, whatever's given. Unfortunately, they will not always work. So we want to make sure that we have alternative versions. And lastly, this one is unrelated, but a little segue into another question that we're going to go over. Do you know how to find the distance in speed? Okay, hopefully you remember how to do that. We'll go over it, but that takes us to our next definition, 212. The average velocity. We're going to use S of t for the position function, right? And we're going to give you an interval over a certain amount of time, starting from left to right, where the a and t is going to be given some time. Okay, so that average velocity is equal to the change in distance over the change in time. And this is called a delta. It's just like a little triangle. It's a Greek letter because remember, the distance is equal to rate times time. And if we're trying to find the rate called velocity, we would have to take that and divide both sides by t to get our rate, which is the distance over time. But if we're trying to find the average velocity, then we will take the change in our distance over the change in our time, which sounds familiar, doesn't it? We can actually write this as, does that appear to look familiar to you? I hope you all got really excited and said, yeah, that's our slope. So as we mentioned very early on in chapter 1, slope lines, very, very important, as you can see today as our introduction to calculus. We're talking about the slope of a line, whether it's a tangent or a secant. We're talking about slope now giving us an average velocity. I mentioned this before, talking about riding my bike to work. We came up with that 10 miles per hour, but that was my average. I didn't get on my bike and start going 10 miles an hour immediately. I didn't pull into the parking lot at 10 miles an hour. It was the average given the distance and the time it took to travel that distance. So where are we going with this? Well, we don't want to be average. All right, people. What if we wanted to know at a certain instant what our velocity was? Check out 213. This one is the instantaneous velocity. But now, instead of over an interval, which was what we found for our average, now we want to find at a specific time. So we're going to say where t is equal to a for that, again, position function. But how do we do that? We know that the change in our distance over the change in time gives us our average velocity. But now we want to find, instead of over that interval, we want to find it at a specific time to get the instantaneous at that instant. So if we wanted to find slope, remember if we had 2 points, we could do that. But now we want to take those 2 points and make them 1 at one instant. So hopefully you were able to come up with, as our change in our time goes to one specific time, or written a little bit simpler, the limit of our position function over some time as our time approaches some value we'll call a specific time. That is our instantaneous velocity definition. Keep moving along here. Make sure you have that written down and highlighted. Something we will definitely go over more frequently down the road. So now we need to move to the second part of this introduction, which is, I know, getting a little long. How about the area problem? Well, the area problem is one that we will get into much, much later in the course. Actually, not until about chapter 4 will we introduce it. So we'll dabble here and there, but here's the gist of it. If we have some function, some curve, right, and we pick some interval from A to B, and we wanted to find all of the area to the x-axis, or we can change that up and we will down the road. How would I find this area? Well, there's a problem. One is we could take this and maybe cut it into two similar looking things, like a rectangle. We could definitely find that if we knew the height here and we knew the difference between these. That would be my base. We could find that area, and then maybe we could take the top part and maybe create a triangle. That's pretty close. Problem is, how am I going to find this little area then that we're missing? We'd know this, we'd know this, but what about that? Problem is, we're given this curvy part, and we know how to find like a trapezoid, things like that, but not with tops that are curvy. The only thing that we really knew was a circle, and if we tried to do a circle in this, we're still going to be off some. We'll have a little too much area, actually. So what we're trying to do is find the area under something that's not geometrically able to be found like we've done in the past with many different shapes. So what we decided to do is try to figure out, well, what of those shapes could we kind of generalize this with? And what would you think? What would be the easiest of all the polygon shapes that we've dealt with? It was the square, because you only needed to know one side and you could find the area of a square. The problem is squares are tough to form because you have to have the exact same base and height. So what we're going to use is what I like to say is its cousin, a different kind of square stretched in one direction. We call it the rectangle. That's the next best thing. And you know how to find the area of a rectangle. It's just length times width or base times height. So let's go look at this graph again, but let's form a bunch of rectangles. Now I said a bunch, how many? Well, it's actually up to you. You can see that this is much better because now we have just these little gaps and actually a little excess. And hopefully those will offset, but what would have been even better than making these 9 rectangles? How about 19? What about 900? Yeah, that's going to be our task. And if you can't figure out where we're going with this by now, keep reading on this stuff. Maybe rewatch this video when I'm going over the GeoGebra things, because we're going to introduce a limit approach to this as well. So again, I won't go into too much detail with this just yet, but just wanted to introduce the two main topics that introduce calculus, and we will try to find all of those rectangles by using this thing called a Riemann sum, named after a fellow German mathematician, Riemann. But we'll be able to form these rectangles and decide how many we want to do. And in order to find their heights and their bases and all that, we'll cut them and create them by using the left, middle, and right approach in order to form these things. Again, I'll go over it in more detail when we get there, but just introducing it now. We will use the limits that we're learning in depth in this chapter, as well as this new symbol and concept that we will call an integral later on down the road. But for now, let's keep working on limits. Let's check out chapter 2, section 2 in the next video to continue with our idea of a limit. Until then, take care, everyone.